So what happens if the reaction has two reactants versus one? So we're going to use the exact same method because we need to know what is the order for each of the individual reactants, but it's important to pick experiments where one is held constant and one is changing. So first, let's just write our rate law. All right, so let's just do A first. What we're looking for is we want A to change, and we want, what we mean by A changing, the concentration of A is the change, but B held constant. So let's look at the 4 different experiments and pick the one where B is constant and A is changing. That looks like experiments 1 and 2. So let's just do the exact same method. We have rate 2 divided by rate 1 is equal to K times the concentration of A2 to the nth power, K concentration of the first experiment to the nth power, and now we can plug everything in. All right, those K's are going to cancel. I get 4, because 8.16 times 10 to the minus 3 divided by 2.04 times 10 to the minus 3 is equal to 4, is equal to 2 to the nth power. So if I replace that n with a 0, 1, or 2, what value does n have to be for this to make sense? It's going to have to be a 2, because 2 squared is equal to 4. That tells us that the rate law or the rate order for A is going to be 2. So I'm going to change the n up here to a 2. Now let's do that same method for B. So A needs to be held constant while B is changing. So that's going to be experiments 2 and 3. So rate 3 divided by rate 2 is equal to K concentration of B3 to the nth power, K B2 to the nth power. So now let's plug everything in. 1.63 times 10 to the minus 2 divided by 8.16 times 10 to the minus 3 equals K times 0.05, K 0.025. So I get 2 is equal to 2 to the nth power. So m can only be 0, 1, or 2. So what number is m for this to make sense? It's going to have to be a 1. So A is going to be a second order, and B is going to be first order. So now I can rewrite my rate order to reflect what we just learned. So now we can actually solve for what our rate constant is. We discovered that the rate law is equal to K times A squared times B. And I want to isolate K and get it by itself, so I'm going to divide by the concentrations on both sides. So that gives me K is equal to rate divided by A squared times B. So I'm going to pick any random experiment and plug it in. They should all give you the exact same value. So I'm going to pick experiment 2. K is equal to 8.16 times 10 to the minus 3, and that's molarity per second, divided by 0.05 molarity squared times 0.025, and that's just molarity. One of these molarities are going to cancel, and I'm going to be left with 1 divided by seconds, and then also 1 divided by molarity squared. So my K value, or my rate constant, is going to be 131, and that's 1 divided by seconds divided by molarity squared, because I have to square my molarities here. But I can write that as m to the minus 2 times second to the minus 1, or 1 divided by m squared times second. However you want to do it, you're fine. As long as you know how to do the actual K value is most important. The units are more tricky. Here's a table to make your life a lot easier when it comes to units. It's really important for you to be able to calculate that rate constant value, but if you're getting a little tricky or you're getting a little bit nervous about the units, this is a great way of making sure your units are correct. So if you find that your rate laws look like this, then your units for your K value will look like that. So for instance, the one we just did, our rate law looked like that, and so our units matched up. So if you don't want to actually do the math on the units, just make sure you have this table available to you, and you can always make sure you have the correct units. So this will save you a lot of time.